Hi there, this is Waves Lesson 9. This one's on ultrasound, so this will be split into two parts. So ultrasound waves have a very high frequency, higher than the upper limit for human hearing. So the range for human hearing is typically between 20 and 20,000 hertz or 20 kilohertz. That'd be if you're relatively young. As you get older, your hearing will degrade, so your range might be, you might stop hearing at 18,000, 17,000, whatever it might be. There's a lot of hearing tests online. I'll link one in the description if you want to have a go at it. So let's start with this question. So what would be the wavelength of a 1 megahertz ultrasound wave? Typical speed 330 meters per second. So you want to pause and have a go at that one. So wave speed equation, V equals F lambda. Wave speed is frequency times wavelength, and we need to rearrange to make wavelength the subject, so we need to get rid of a times F. So to do that, we divide by F on the other side. So wave speed is 330 divided by the frequency, 1 megahertz. So 1 megahertz is 1 million, so you could write a 1 with 6 zeros, or you could just write 1 times 10 to the power of 6. Which is probably more useful because a lot of your answers for this stuff will actually, or could probably come out in standard form anyway. So that'd be 330 divided by 1 times 10 to the power of 6, which will give you 3.3 times 10 to the power of minus 4 meters. If you got that, well done. All right, let's move on. So ultrasound waves are partially reflected when they hit the boundary between different materials. Remember, waves can do three things at a boundary. They can either be reflected, transmitted, or absorbed. So what do we call it when sound waves reflect back to us? Can you think about that one? It's an echo. And what happens to the sound energy that is absorbed? So what do you think happens there? Well, you get a mechanical vibration, and normally you get some heat being developed as well. So you get a transfer of energy into thermal energy through the mechanical vibration. All right, let's move on. So we can use ultrasound to clean objects or to break them down. So here's an example of ultrasonic cleaning or ultrasound cleaning. It's called ultrasonics in industry, but we, for GCSE, we call it ultrasound. So there's a few before and afters, as you can see. It's quite the thing. It works very effectively. It's using all kinds of things, teeth cleaning. Hygienists will use, they call them ultrasonics. Really fast vibrations, obviously break down all the dirt on your teeth. So what else can they do? Really good for kidney stones, so they break them down. So kidney stone symptoms, if you get a pain deep in your back, sharp and a deep dull ache, could be indicative of kidney stones. So doctors will test you, and if you've got kidney stones, simple ones which are too large to pass through into the urine, they just use ultrasonics or ultrasound waves, breaks them down into much smaller pieces, and then you can pass them out normally in urine. If they're not simple and the larger, I believe, I'm not a doctor, but I believe it's surgical intervention. So obviously, if you get anything like this, treat it as quickly as possible. All right, let's move on. So a question here. I'm not going to give you the equation that you need, but I just want you to pause and have a go at this one. If you need the equation, I'm going to take you through this question anyway. You could use it as an example. So the time taken for the reflections to reach a detector can be used to determine how far away such a boundary is. So submarines use this as sonar. So example, a pulse of ultrasound takes 4.5 seconds to travel from a submarine and back again. That's important. How far away is the seabed? And the speed of sound in seawater is 1,520 meters per second. So we're going to use distance is speed times time. So we need to calculate the distance. So the speed is 1,520 meters per second multiplied by the time, 4.5 seconds. So that gives us 6,840 meters. Now that is the distance that the pulse is sent and then comes back up. So we obviously only want the distance to the bottom, so we need to half that value. So the distance to the seabed is 3,420 meters. If you got that, really well done. If not, treat that as an example. And then I've got 3 more practice questions for you to have a go at. So if you want to pause and attempt these, some of the units are a bit tricky. All right, I'll start going through them. So a fishing boat uses sonar to detect a shoal of fish underwater. That's just a group of fish. A short pulse of sound is emitted from the boat and it is detected 0.1 seconds later. How far below the boat are the fish? So speed of sound is given in kilometers per second, 1.5. All right, let's go. So distance is speed times time. So the speed is 1.5 kilometers per second, which is 1,500. Multiplied by time, 0.1. So that gives us, that's a tenth. So we need to divide that by 10, so that's 150 meters. Now again, that's the distance from the ship down to the fish and then back to the ship. So we need to divide that by 2. So the total distance of the fish would be 75 meters. Number 2, a bat is chasing a moth. It sends out short squeaks of sound and listens for the echoes. If it takes 2 ms, which is milliseconds, for the echo from the moth to return, how far away is the moth? Speed of sound in air, 340 meters per second. So we need to do distance is speed times time. So the speed is 340, multiplied by 2 milliseconds. So you'd have to divide by 1,000. So you could just do 2 divided by 1,000, or you could do 2 times 10 to the power minus 3. So that gives us 0.68 meters, but obviously that's the return journey included, so we need to divide that by 2. So the distance to the moth is 0.34 meters. Now the last one is a bit of a show me question, so I've left the answer on there, if you noticed it. So that's the answer. The question is, how would you get that answer, or how would you show that? So number 3, a scientist is trying to determine the speed of sound in a new material. She knows that the material is 12.9 millimeters thick because she could just measure it. And she can measure the time taken for the ultrasound pulse to return as 15 microseconds. So I'm going to draw a little diagram to help with this. So here's the material. So it's 12.9 millimeters thick. Now the ultrasound will be sent out from a device from the top. It's got to go down and come back up. So the actual distance that the wave will travel is 12.9 millimeters times 2. So that's 25.8 millimeters. And we actually need that in meters. So you could either divide that by 1,000, or you could simply write 25.8 times 10 to the power minus 3 meters. Now the microseconds might be a bit tricky. 15 microseconds, well, there's a million, so you have to divide it by 1 million. Or the time could be 15, and instead of dividing by a million, just put 15 times 10 to the power minus 6. Now if you're good at maths and understand a form, you might be screaming, thinking that should be 1.5 times, that's in maths. 15 microseconds doing 15 times 10 to the minus 6 is totally normal in physics or engineering. Seconds. Then we just need to get speed. So speed is distance over time. So you need to do your 25.8 times 10 to the minus 3 divided by the time, 15 times 10 to the minus 6. And if you calculate that, you will get the 1,720 meters per second. Now figure that out, you've done really well there. That'd be a very high level question. Hopefully that's gone well, and thanks for watching.